The next dinosaur is more peculiar. One reason for its peculiarity is its appearance, and the other is its origin. Most of ceratopsians we introduced before were from North America, and the next one is called Sinoceratops. They lived in Zhujiang, Shandong province, and was the ceratopsid species found outside the Americas, which broke people's previous understanding of ceratopsians. We thought that ceratopsians might have originated in Asia, like Psittacosaurus or Protoceratops. Many primitive ceratopsians were found in China, but very few in North America. In the age of dinosaurs, the northern continent was unified, so it was believed that ceratopsians might have originated in Asia, because the very primitive species basically lived in Asia. After originating from Asia, it migrated to North America, and some ceratopsian dinosaurs that migrated to North America slowly evolved into giant ceratopsids, which was what people believed in early years. It was thought that ceratopsids might have never left North America, and only lived in this area, and then the continent was torn into pieces with oceans in between. They might have been isolated there, so no ceratopsids have been found outside of North America. Until 2009, when scientists named a species of dinosaurs Sinoceratops in Shandong, we realized that we had to change the view that ceratopsids originated in Asia but lived in North America. It was probably because that no ceratopsid fossils had been found outside North America before. In fact, ceratopsids also lived outside North America. Sinoceratops had the features of centrosaurines. They had a shorter face, a well-developed nasal horn on the nose, and no brow horn. In addition, like Centrosaurus, their head frills were rich in changes. The fossils of Sinoceratops are not well preserved. At present, the two skulls are relatively incomplete, one of which has the face and nasal horn, and the other has the head frill. There were many hook-like structures on their head frills. Such hook-like structures have been found on other ceratopsians before, but few had cut downward like Sinoceratops. All its horns were forward and downward, like a human hand grasping. This is the most unique feature of Sinoceratops. It had a large body, which could grow up to more than 6 meters in length and weigh up to 5 tons, making them really huge. In addition, Sinoceratops shared some features with Pachyrhinosaurus. The faces of most ceratopsians were relatively narrow, while ceratops were very wide, and their noses were especially wide, a bit like Pachyrhinosaurus, forming a huge bony base with various lumps, some of which were like small short horns, in the middle of which was a spike. Since Sinoceratops lived far away from the previously introduced centrosaurines, their developmental system might not be the same as that of the centrosaurines in North America. We can see an almost complete evolutionary process of centrosaurines in North America. For example, Centrosaurus evolved into Styracosaurus with many spikes on their heads. Another branch is a Neosaurus with horns curved downward, which then evolved into Pachyrhinosaurus. We can see that their evolution is coherent. However, in Sinoceratops, there were several comprehensive features of other ceratopsians at the same time, which indicates that its evolution process might differ from that of ceratopsians in North America due to geographical isolation. But to support this view, more ceratopsians need to be found in China or elsewhere in Asia, because there's only one specimen in China at present, and we can't do a systematic evolutionary analysis. After the introduction of Sinoceratops, the introduction of the centrosaurines is temporarily over. Next, let's move on to chasmosaurines. Next, let's take a look at Cosmoceratops. The upper part of their head frills drooped down like a human bang. They had many decorations on their head frills, and the outermost grew outward and were very long, which could be seen in centrosaurines, but were very rare in chasmosaurines. Also, the drooping part was almost against the surface of the frill, so it was definitely not for defense, but for show. We know that some parts of ceratopsians, such as the frills and horns, had some keratins when they were alive. Keratins are very important for modern animals. First of all, it can enhance the strength of biological parts, and its colors are brighter. The animals with keratins we see today, such as turtles, generally have bright patterns on their shells. On some birds, the keratinous parts such as the mouth of toucans, the casque of hornbills and cassowaries, also have bright yellow or other colors that make them look brighter. Therefore, after the surface was covered with keratins, Cosmoceratops frill might also show a brighter color, that is to say, they used the keratinous structure to form the pattern on the head frill, which could enhance the defense. Because the head frill was hollow inside, thus not quite defensive. Next, let's move on to Chasmosaurus. The Chasmosaurini was named after Chasmosaurus, which was the typical representative of this subfamily. The biggest feature was their head frills, which were square or rhomboid, that grew on both sides. Its name means opening lizard because there were large openings on their head frills. Chasmosaurines all had very large head frills, and we can't strictly say that their head frills were not protective. When encountering predators that had never preyed on ceratopsian dinosaurs, their head frills had a certain intimidating effect, making predators think that biting their necks was not feasible, because hitting their head frills would be very painful. Once they were preyed on, the deception was exposed, and predators would find that their frills were hollow inside and no longer protective. Just a joke. The main function of Chasmosaurus head frills might be for display. When they were alive, their head frills probably had very ornate patterns and brilliant colors, like a peacock's plumage. There is also a theory that their head frills might play a role in cooling, which can refer to today's African elephants. The ears of African elephants are much larger than those of Asian elephants, because Asia is relatively high in latitude and low in temperature, and Asian elephants generally don't use their ears to dissipate heat. The ears of African elephants are good tools for dissipating heat, because they are covered with capillaries. Perhaps when ceratopsians were alive, their head frills also played such a role. Let's look at the facial features of Chasmosaurus. They had not a very developed nasal horn, and their brow horns were not like those of other Chasmosaurines. The typical representative of Chasmosaurines didn't have brow horns. This is the conclusion after the later research. In the early years, people didn't pay attention to these features when they named the Centrosaurini and Chasmosaurini. After research and more fossils have been excavated, many of the reasons for naming and classification in the first place have constantly been subverted. Just like the classification of dinosaurs we are talking about today, the Saurischian and Ornithischia. In the early years, people simply thought that the pelvic structure of Saurischians resembled that of lizards, while the pelvic structure of Ornithischians resembled birds. Saurischians had one pubis pointed forward and the other, ischium, backward, like lizards, while Ornithischians had the two both faced the back, a bit like a bird's pelvis, that forms a circle. In the early years, people simply used this to name dinosaurs. But later, we found that birds are actually very closely related to the Saurischian, but not related to the Ornithischia at all, so were Theropoda and Ornithopoda. In the early years, people simply believed that the claws of Theropoda were sharper and more like beasts, so they were called Theropoda, which means wild beast feet. The ornithopods had 3 toes on their feet, a bit like today's birds, hence they had their name, meaning bird feet. But now we know that classifying dinosaurs by feet alone is not very reliable. Chasmosaurus didn't have well-developed brow horns. There are 2 kinds of Chasmosaurus that we currently know. One is Chasmosaurus belli, and the other is Chasmosaurus russelli. One big difference between these 2 is their brow horns. The one on the picture is a typical Chasmosaurus russelli, with small brow horns, which look cute, but Chasmosaurus belli had no brow horns at all. Whether or not there were brow horns is a very difference between these 2 species of Chasmosaurus. In addition, in the past, there was a species of Chasmosaurus with very long brow horns. Later, after research, it was found that it didn't belong to Chasmosaurus, although the shape of their head frills was very similar to that of the other 2 species of Chasmosaurus. Now it has become an independent genus of ceratopsians called Mogoceratops. After introducing Chasmosaurus, let's take a look at the familiar Triceratops, which is the representative of Chasmosaurines. It had a very large head frill with 3 horns. It had 2 brow horns that grew out of the eye sockets, and a small nasal horn. In addition, it had a parrot-like mouth, which was also a feature of ceratopsians. One of the more special features of Triceratops was their head frills. Although their head frills looked similar to those of the ceratopsians introduced earlier, the difference was that their head frills were solid. Triceratops' head frills could indeed play a defensive role. We've found wounds on the head frills of many Triceratops, some caused by Tyrannosaurus rex, and some caused by other Triceratops. Therefore, their head frills could be used for defense, and they could also play a display role when they were alive, which was very different from other ceratopsians. The solid head frills added weight to the heads, and we found that the skeletons of Triceratops tended to be thicker than those of other ceratopsians, especially the forelimbs. The forelimbs of other ceratopsians were often relatively thin, but the forelimb skeletons of Triceratops were very thick, which might be caused by the weight of the head. Triceratops is one of the ceratopsians that we've found a lot. Most ceratopsians had no skin preserved, and only a few did. For example, in the previously mentioned Pachyrhinosaurus, only a few scale fossils on the legs have been preserved, and some skin fossils of Chasmosaurus have been preserved. The situation of Centrosaurus is relatively good. The skin fossils on one side of its body have been preserved. These dinosaurs all had very delicate scales. The skin of Triceratops was very well preserved, and the fossils show that the scales of Triceratops were very large, as the size of eggs. Its scales were like paved pebbles, which was very different from other ceratopsians. In addition, we also found many fossils of young individuals of Triceratops. The picture shows a Triceratops with a baby. The face of the baby Triceratops was very short, the horns on the head were still small spikes, and the head frill was not fully developed, and its frill grew downward at first. Analysis has shown that the horns of juvenile Triceratops tended to grow upward, were relatively slender and curved upward, and those of adult Triceratops were slightly downward sloping, which might account for functional differences during growth. The horns of juvenile Triceratops were mainly for display and were more slender. As adults, their horns became thicker and protruded forward, which might play a role in attacking intruders. After talking about Triceratops, let's look at Torosaurus. Torosaurus looked a lot like Triceratops. Their faces were very similar to those of Triceratops, with 3 horns. Although the nasal horns of some Torosaurus were small cones, like those of Triceratops, most Torosaurus had flat, not very pointed and triangular nasal horns, which was a feature of Torosaurus. Torosaurus had much larger head frills than Triceratops. Similar to Triceratops' head frills, theirs were round, but elongated. Triceratops had a lot of processes around their frills, but the frills of Torosaurus were flat, short, and quite different from those of Triceratops. And their head frills were hollow, as flashy as those of most Chasmosaurians. They had very huge head frills, but there were 2 large openings in the middle. The size of the openings was smaller than those of Chasmosaurus, which were not that fragile and were relatively strong. In the past, it was believed that Torosaurus was the full adult state, or aged form of Triceratops, because people had not found the juveniles of Torosaurus before, and Torosaurus and Triceratops were too similar. At a certain stage of growth, the head frills of Protoceratops would suddenly become larger, so some scientists speculated that Triceratops might be the juvenile state, and maybe at a certain stage of growth, their head frills would suddenly become larger, forming 2 openings and become the look of Torosaurus. Only a handful of scientists agree with this claim. It was not until later that people discovered the skull of a juvenile Torosaurus. The head frill of this specimen was already very large with big openings, making it fundamentally different from the Triceratops of the same age. So now we know that Torosaurus and Triceratops are indeed 2 completely different genera with essential differences. There are not many other preserved fossils of Torosaurus, most of which are skulls and some limb bones. We mainly relied on the fossils of Triceratops for reconstructing their other body parts. But one thing is clear, When they were alive, the head frills must look more ornate than Triceratops, because their head frills were hollow, more displaying than defensive. After introducing so many ceratopsians, let's look at this picture. The reconstructed image we are looking at is the living state of Triceratops and Torosaurus. Both of these dinosaurs were among the last dinosaurs of the late Cretaceous, especially Torosaurus. Its specimen was what we've found closest to the time when the dinosaurs went extinct. The most prominent in the picture is a Tyrannosaurus rex, the top predator in their area, feeding on most animals they could see. But animals such as Torosaurus and Triceratops were not the first choice for Tyrannosaurus rex, because they had relatively sharp horns and head frills, making them quite difficult to capture. Some small animals in the picture, such as dromaeosaurids and oviraptorosaurs, were not the prey objects of T-Rex because they ran relatively fast. T-Rex might prefer to prey on dinosaurs such as hadrosaurs, that were not very fast and didn't have much decoration on their bodies, such as the two Augustinolophus in the far distance in the picture. Although they were very large, in the process of growth and development, their body size must have been relatively small at a certain stage, suitable for T-Rex to prey on. We can see that the entire landform and plant environment of the Cretaceous is very close to what we see today. The only difference is the dinosaurs. 66 million years ago, with the death of the last Torosaurus, there has never been an animal as amazing as the ceratopsian family on Earth. Next, let's get to know our protagonist, Aubrey, the Torosaurus 135 scientific art model, which is based on a very complete skull of Torosaurus. In the past, we were inaccurate in the reconstruction of their skulls. Although they were discovered a long time ago, the fossils of their faces were generally broken. In the early restorations of Torosaurus, their faces were very short, and we could see a fairly long head frill, but the front was very small, which looked exaggerated and disproportionate. We didn't know what it looked like until the relatively intact skull of Torosaurus was discovered in recent years. It had a very long and narrow face with a triangular nasal horn, as shown in the model. From the front, we can see that it looks like shark fins, not cone-shaped like Triceratops. In the specimens of Torosaurus, their horns were generally curved downward, unlike those of Triceratops, which were S-shaped. Although they had drooping horns, most specimens of Triceratops had S-shaped horns. Let's look at Doyle, the Triceratops, which came from a well-known specimen, and its fossils show that its horns were S-shaped, but the horns of Torosaurus were not. From the front, the horns of Triceratops were relatively wider, but Torosaurus resembled shark fins. There are two species of Triceratops, Triceratops horridus and Triceratops precisus. The mouth and nose of T. precisus were shorter, and its nasal horn was rounder and longer, while T. horridus' nasal horn was smaller, and closer to that of Torosaurus. Therefore, we now generally think that Torosaurus might have a closer biological relationship with T. horridus. I've mentioned the sizes of their head frills just now. From the two models, we can clearly see the differences in the size and shape of their head frills. The head frills of the Triceratops specimens were relatively short, except for a few individuals. Torosaurus was just the opposite. Their head frills were very long, and the frills were very blunt and flat, unlike Triceratops, whose frills were relatively sharp, and some were even hornlets. Another difference is that some Triceratops had relatively developed jugal horns, but this was not the case for Torosaurus, whose jugal horns were short, and although most of their frills were flat, the bottom two were sharper and protruded forward. In addition to that, Triceratops had solid head frills, while Torosaurus had two openings in their head frills. Unlike Chasmosaurus, who had a large triangular gap, Torosaurus had had its frill rounded in the upper part. When designed its surface pattern, we put it right above the openings, with two eye-like patterns. This pattern is very common in today's animals, called eye spot, which can appear on the bodies of small insects and large birds, such as the feathers on the back of peacocks, or fan feathers to be precise. When a peacock is in its pride, there are some patterns similar to the eye spot. Generally, it acts as a kind of intimidation, reminding other carnivorous dinosaurs that I'm watching you, and you'd better not attack me. Having said that, I have to mention a hypothesis from recent years. In recent years, studies have suggested that species with eye spots, such as butterflies or moths, may have their eye spot that mimics the eyes of dinosaurs. These insects originated in the age of dinosaurs, and the fossil records show that some fossils preserve traces of eye spots, not much changed from their descendants today. Since it originated in the age of dinosaurs, the species they simulated must be the species at that time, so if we want to know the eye shapes of dinosaurs, we can observe moths or butterflies, and we may see the original eye shapes of dinosaurs. This is off topic. Let's take a look at the juvenile state of Torosaurus. Here is one example. Earlier we mentioned the discovery of the skull of a juvenile Torosaurus, so we can be sure that Torosaurus was not Triceratops in full adult state. As we can see from the two models, their facial shapes were also different. Regarding their mouth shapes, Torosaurus was shorter, and Triceratops was generally hooked. The two heads look similar at first glance, but there were too many essential differences. The skulls of juvenile Torosaurus show completely different features from those of Triceratops, and in the juvenile state, they already had rather large head frills and openings. Therefore, we believe that Torosaurus head frills developed faster than Triceratops. Therefore, in the restoration of the juvenile Torosaurus, although their heads mainly based on those of Triceratops, the juvenile Torosaurus and Triceratops in the same stage were very different in terms of head frills shape and style. First of all, the shape was close to that of adult Torosaurus, narrow and long, while Triceratops tend to be round. In addition, we can see that they did not develop nasal horns in their infancy, but their brow horns had grown into small spikes. The horns on the juvenile Triceratops skull grew upward, with a small, upwardly curved spike. In our design, the horns of the juvenile Torosaurus were hooked downward, because current research believes that the horns of Triceratops first curved upward when growing, and formed elongated upward hooks in the juvenile stage, and then with the growth of age, the root of the horns bent downward, and the whole grew downward, forming an S shape. Later studies on the tomography of Triceratops skull horns also corroborated this. Later, we found that, when the keratins of Triceratops horns grew, they grew forward layer by layer. This means in childhood, their horns grew upward, and as Triceratops got older, after this section had grown, they curved downward again to form an S shape. But according to many of the specimens of Torosaurus we've seen so far, their entire horns were curved downward, so the juvenile's horns didn't have a stage of upwardly curved growth. When designing the juveniles, we made them curved downward, different from Triceratops. The restoration of Torosaurus body mainly borrowed ideas from Triceratops, because we don't know much about it. The fossils of Torosaurus phylums have been mainly preserved, which are not much different from Triceratops. They had 5 fingers, the front 3 had hooves and the other 2 didn't. When walking, they mainly relied on the front 3 fingers for weight bearing, and the other 2 were auxiliary. Some incomplete, early footprint fossils of phylums show that they only had 3 or 4 fingers touching the ground. In recent years, according to some well-preserved fossils, we found that, when they walked, all 5 toes touched the ground, but the last had no nails and did not bear weight. In the early years, when restoring such dinosaurs, people restored the soles of their feet into circular pads. Now, based on relatively new footprint fossils, we believe that their soles were hollow, horseshoe-shaped, and their hind legs were 4 toes plus a pad. The skeleton fossils of Torosaurus were incomplete, and their skin fossils have never been found, so their skin restoration is mainly based on Triceratops. They had relatively large scales, but compared with Triceratops, their scales were relatively smaller and more delicate, which was also a difference between them and Triceratops. Their abdomen were also restored based on Triceratops, which had scales close to the grids arranged in rows. Their mouth could open wide, and recent anatomical studies have suggested that they might have no cheeks. Their jaw muscles started here and extended up to the head frills, allowing their mouths to open wider. The carnivorous dinosaurs that needed to hunt could open their mouths very wide, while dinosaurs such as Torosaurus only ate plants, so their joints did not open that much. Their faces were very long, so they didn't need to open their mouths too much, supporting newer muscle research that suggests that they didn't have cheeks. If they had cheeks, the mouth opening of this dinosaur could cause a 50 centimeters deformation in length. But their skins were scaly and not that elastic. Moreover, this dinosaur didn't have much flesh on its face, so it probably looked like this. It might be true that they didn't have cheeks. There are also some interesting points. The eyes of dinosaurs like Torosaurus had a layer of bone rings like swimming rings, and so did Triceratops. The eye sockets were wrapped in keratins, which were a bit close to today's antelopes. Antelopes' eyes protrude from the bone rings, not completely, but the whole eyes bulge a lot, which is conducive to their observation of the surrounding area, improving their field of vision and making it easier for them to prevent predators from attacking. The same thing goes for Triceratops and Torosaurus, whose eyes might have bulged outward. Both these two genera of dinosaurs had very large head frills that blocked the view from behind. Therefore, some scholars believe that they had a solution, which was to have a gap between their jugal horns and the sharp horns at the end of their head frills. Some scientists believe that this gap helped them turn their heads, and they used their peripheral vision like a rear-view mirror to increase their backward vision in a limited range. That is an interesting point. The restoration of the skin on Torosaurus' body is based on Triceratops, but their head frills might be completely different from Triceratops. People have found very fine bulges that were not scales on the head frills of Triceratops, which were like the kind of particles on the harder rhino hide. The head frills of Triceratops were solid, so they had a certain defensive effect, and they might have had such hard skins. However, if the head frill surface of Torosaurus had complex patterns as we reconstructed, it's possible that their head frills had relatively large scales, because like mosaics or television picture tubes, each of the different colored scales together formed a pattern. We've also found no skin impressions of Torosaurus faces, but there were several regular bulges behind the horns of Torosaurus. There is no relevant article to study these bumps yet, but when we restored it, we thought that they might represent the corresponding epidermis, so I restored them to resemble the scales of crocodiles. These bulges were relatively regular. If there were large bulges on the faces of animals such as Gila monsters today, they often correspond to large scales of the same shape. Therefore, in this area, I adopted this restoration. Good, the above are some introductions about Aubrey the Torosaurus. Thank you all.